Aside from the top-down lithography such as photo or e-beam lithography, another approach based on bottom-up way have been widely employed for a variety of research and development at relative inexpensive cost. These bottom-up like lithography is called unconventional lithography or simply soft lithography. For example, there are various soft lithography methods such as nanoimprint lithography as shown in the upper left figure, microcontact printing as shown in the upper right figure, capillary force lithography, polymerization-based replication as shown in the lower left figure, and microcontact printing as shown in the lower right figure. Microtransfer molding is one of the simplest method of soft lithography. In microtransfer molding, excess liquid is removed by scrapping with a flat PDMS block or by blowing off with a stream of nitrogen. Due to its simplicity, it can be used for multiple times to fabricate three-dimensional microstructures such as shown in the right figure. Using wave physics of intervened by the mold as a phase mask, it is possible to control the interference pattern beneath the mold to pattern the underlying layer. This method is called as phase shifting photolithography. In microcontact printing, we can use printing on a planar surface with a planar stamp as shown in A, or large area printing on a planar surface with a rolling stamp as shown in B, or printing on a non-planar surface with a planar stamp as shown in C. For ink, solution of hexadecanethiol in ethanol with concentration of 100 millimole can be used with a contact time of longer than 0.3 seconds, enough to form highly ordered self-assembled monolayers on gold surface. For micromolding in capillaries, PDMS mold works as a microscale channel. For PDMS mold is placed on the surface of a substrate. The relief structure in the mold forms a network of empty channels. Liquid pre-polymer used here should have low viscosity. The liquid spontaneously fills the channels by capillary action. There are several limitations in this method. Isolated structure cannot form channel network. In addition, the rate of filling over a large distance decreases. Finally, the gas in the channel appears to be escaped by diffusing into the PDMS. Here are some illustrations for you to understand what exactly the soft lithography. For example, let's look at the microcontact printing as shown in the leftmost figures. As implied in the name, microcontact printing uses the polymer mold such as PDMS mold as a stamp. For stamp solution, you can use various kinds of solution from quantum dot solution to protein solution. The stamp can be placed onto the designated substrate with alignment and pressed. After pressing, the stamp is released. For the perfect printing-driven patterning, it is important to prepare the stamp with surface treatment targeting anti-sticking. The second one is nano-imprint lithography as shown in the second case from the left. As was used in microcontact printing, nano-imprint lithography used mold as a stamp. However, the mold is hard for the pressing into the pre-deposited polymer or inorganic substrate. For the mobility of the being pressed layer, the process can use higher temperature or solvent atmosphere. After releasing the mold, the underlying pressed layer is developed and treated for hardening. In the third case, soft molding-assisted nanoimprint lithography uses pre-cured liquid droplet and soft mold for micro-patterning. After curing and stamp release, one can make replication of the master mold. In the fourth case, micro-molding in capillary using the soft mold for microchannel, into which solution of polymeric fluid can flow driven by capillary force. This method is advantageous to form some microfluidic channel network. One of the most promising and extendable to the industry-level soft lithography is nanoimprint lithography. Nanoimprint lithography can pattern large areas such as 12 inches wafers with good quality control. In addition, it is advantageous for production cost reduction. For example, an imprint mold can be used thousands of times. There are two types of nanoimprint lithography. The first one of thermal nanoimprint lithography. For the patterning, thermoplastic polymer thin film is coated on the substrate. Thermoplastic polymer thin film is moldable above a specific temperature and solidifies upon cooling. Onto the surface of the coated polymer thin film, mold is pressed. The mold is usually in silicon, made using photo or e-beam lithography and with anti-sticking coating. During the imprinting, apply heat and mechanical press. Next, cool down and separate the mold. Finally, etch residual resist. Thermal nanoimprint lithography has smaller resolution than photolithography down to 20 nanometers. The second one is UV nanoimprint lithography. This lithography is similar to thermal nanoimprint lithography. Deposit UV-sensitive resist on the substrate. Nanoimprint mold, which is usually in quartz, made using EBL and with anti-sticking coating. Fill and expose. Separate. Etch residual resist. UV nanoimprint lithography has smaller resolution than photolithography down to 10 nanometers as shown in the electron microscope image of silicon dots with 10 nanometer diameters in the middle figure. There is another unconventional lithography called as nanosphere assembly lithography. In this method, nanospheres with diameter is several hundred nanometers are assembled to form close-packed two-dimensional or three-dimensional structures. We can stack double or multi-layered assembled nanospheres for specific purposes. Due to the close-packed geometry, there exists specific shaped voids with periodic array, and the feature can be determined by the number of stacked layers. For example, as shown in the right figure, void size can be controlled as a function of stacking number.